All right, on to chapter 12, where we apply bonding to physical properties. So let's talk about heat of vaporization. How much water in grams can be vaporized at its boiling point with 155 kilojoules of heat? So ripping water or any liquid from the liquid phase to the vapor phase, you have to break those bonds, and that's the intermolecular forces bond. So actually, higher boiling point means more attractiveness between the molecules. And water has a pretty relatively high heat of vaporization, but we're given energy, and then we've got to figure out how many moles of water we can get from that, and then the mass of water. Right? Remember, you can't forget anything from the previous chapters, so don't drop it from your brains. And here's the heat of vaporization for water. It's 40.7, sometimes referred to as a latent heat. So if you hear the latent heat, it means the same thing. And so we solved it and started 155 kilojoules, mole per 40.7 kilojoules, then 18 grams per mole. And then doing that, we get 68.6 grams. So, and let's do this for ice as well. So calculate the amount of ice in grams that upon melting absorbs 237 kilojoules of heat. So same idea, but now I mean heat of fusion instead of heat of vaporization. And heat of fusion of ice is 6.02 kilojoules per mole. And it's really just the same as the previous problem, except for we use the heat of fusion instead of the heat of vaporization. And then we get 709 grams using that. So, and the units correct? Yeah, units are correct. Does it make sense? Yeah, especially considering the last one, that the other value is 7 times as large, and there's also more energy, right? So this makes sense. So talking about dispersion forces. Dispersion forces, they scale with mass. So the more mass, the more polarizable the electron cloud is. So there's more electrons, and they're able to move around more. Also the shape. So the flatter molecules have greater dispersion forces than the spherical ones. But generally speaking, for this class, and it works under almost all circumstances, the mass is the deciding factor here. Besides that, chlorine and iodine, they're both relatively they're shaped kind of like Tylenols, kind of they're diatomic molecules. They have the same shape, kind of thing. So chlorine's mass is around 70 grams per mole, and iodine is 250 grams per mole. So because the iodine has a higher molar mass, it has more polarizability. Therefore, it has a higher boiling point. So, and the boiling point is a measure of the strength of the intermolecular forces. So, indicate whether each molecule has dipole-dipole forces. And for me, with this chapter, this is one of those wow, chemistry is cool kind of moments for me, because I was like, wow, we can do the structure of the molecules, and then we can use the electronic properties of it and to predict physical properties. I'm like, that's so cool. So I really do like this. It's kind of cool. So we have to, for this though, we have to look at the molecule to be able to draw its Lewis structure and determine if the molecule is polar or not, and then from that determine their dipole-dipole forces. And so carbon dioxide, it's a linear molecule. It's completely nonpolar though, so that's not true. That it has dipole forces. So that A is no. I'll show you some pictures coming up, and you can stop the video and look at it a little closer. Dichloromethane here, or methylene chloride. So methylene chloride is in fact a polar molecule. It's tetrahedral, but the atoms are different. Therefore, it's a polar molecule. And so because that has dipole-dipole forces, Methane is tetrahedral. All the atoms are the same. Therefore, it's nonpolar, and it does not have dipole-dipole forces. So it's only B. And here shows you the differences here, and it's also from some of the previous chapters. So, and dichloromethane is the one that's polar of these, whereas methane and carbon dioxide are not. So one of these compounds liquid at room temperature, which one and why? So we have formaldehyde, fluoromethane, and hydrogen peroxide. So if you look at the type of intermolecular force, Formaldehyde is a dipole. Also has dispersion forces. They always have dispersion forces. Every atom and or molecule has dispersion forces. But formaldehyde has a dipole bonding, but it's not going to be as strong. Formaldehyde, generally speaking, is a gas at room temperature. Fluoromethane, it's polar as well, but it's not enough either. And then you have hydrogen peroxide. It's also it's a bent molecule. Hydrogen peroxide is a bent molecule, and all bent molecules are polar. All three of these molecules are polar. The difference is hydrogen peroxide has hydrogen bonding, and hydrogen bonding is when hydrogen directly attaches to a fluorine, oxygen, or nitrogen. So you can see in the fluoromethane, you have hydrogen and fluorine in it, but the hydrogen is not directly attached to the fluorine. Whereas in hydrogen peroxide, the oxygen and the hydrogen are directly attached. And so because of that, it is in fact a liquid. And you probably know this because you can buy a liquid hydrogen peroxide. Of course, the stuff you buy is definitely not 100%. That stuff's pretty powerful. But it's explosive. So, but this is in fact a liquid at room temperature, and it's because of the hydrogen bonding. So, what type of these solids, molecular, ionic, or atomic? Calcium chloride, that's ionic. It's a metal, non-metal. Electronegativity difference more than 2, so that's an ionic bond, an ionic solid. Cobalt is an element. It's going to be atomic. Specifically, it's a metallic bond. And then carbon disulfide. This is a molecular. It's a molecular solid, so it's not going to be ionic or atomic. So, and we are done. Very very short chapter here, huh? So what are you gonna do with your time? The answer is, of course, move on to the next chapter. Thank you for listening.